Look up at the night sky. What do you see? A vast, silent ocean of stars, galaxies swirling in the darkness, and the illusion of something eternal. But here's the truth hiding in plain sight. That stillness is an illusion. The universe isn't just there. It's stretching, pulling apart at the seams like cosmic taffy, expanding faster than we ever imagined. Every second, galaxies drift further away, carried by an invisible force we're only beginning to understand. And the wildest part, this isn't science fiction. It's the reality of our cosmos, a reality that challenges everything we think we know about space, time, and the very fabric of existence. Picture this: 100 years ago, we believed the universe was static, unchanging. Then came Edwin Hubble peering through his telescope, and everything changed. He saw galaxies racing away from us, their light redshifted, their paths marked by an unmistakable signature. The universe wasn't just big, it was growing. But here's where it gets even stranger. Decades later, we discovered this expansion isn't slowing down. It's accelerating, fueled by a mysterious force we call dark energy. Think about that for a second. The cosmos isn't just expanding, it's speeding up, as if some invisible hand is stretching space-time itself. That's the journey we're embarking on today, 30 mind-blowing facts about the expansion of the universe, from the echoes of the Big Bang to the edge of what we can observe. We'll unravel how scientists measure this relentless growth, why distant galaxies seem to vanish before our eyes, and what this means for the ultimate fate of everything. Because this isn't just a story about distant stars, it's a story about us, every atom in your body, every planet, every speck of light in the night sky. It's all part of this grand, accelerating dance. So let's dive in. The universe is waiting. In 1929, Edwin Hubble made an observation that shattered humanity's understanding of the cosmos forever. Peering through the 100-inch Hooker telescope at Mount Wilson, he noticed something peculiar about the light from distant galaxies. It was stretched, shifted toward the red end of the spectrum. This redshift wasn't just a curiosity, it was a cosmic fingerprint, proof that these galaxies were hurtling away from us, and the farther away they were, the faster they receded. It was as if the universe itself was stretching, carrying galaxies along like dots on an inflating balloon. Hubble's discovery didn't just rewrite textbooks, it overturned centuries of belief. Until then, even Einstein had assumed the universe was static, unchanging. But Hubble's data painted a different picture, a dynamic, expanding cosmos, one that had burst into existence and never stopped moving. Imagine the shockwaves this sent through the scientific community. Suddenly, the Milky Way wasn't some fixed stage for the stars. It was a single note in a grand symphony of motion, with space itself as the conductor. The implications were staggering. If galaxies were racing apart, tracing their paths backward would lead to a single, explosive origin, the Big Bang. Hubble's work didn't just reveal an expanding universe, it gave us the first clues to its birth. And yet, even he couldn't have predicted the next twist. Decades later, we'd learn this expansion isn't just continuing, it's accelerating, a revelation that would introduce us to dark energy and force us to question everything all over again. But that's a story for another fact. For now, let's sit with the audacity of Hubble's breakthrough, a lone astronomer staring into the void who forever changed how we see our place in the cosmos. To grasp the mind-bending reality of universal expansion, scientists often turn to a simple yet profound analogy: the inflating balloon. Picture a partially inflated balloon with small dots scattered across its surface. Each dot represents a galaxy anchored to the fabric of space itself. Now, as you blow air into the balloon, its surface stretches, causing every dot to drift away from every other dot. Here's the crucial insight: the galaxies aren't moving through space like cars on a highway. Instead, space itself is stretching, carrying them apart like a cosmic tide. This analogy reveals something extraordinary about our universe. From any single dot's perspective, all other dots appear to be moving away, with more distant dots receding faster, just as Hubble observed. The farther apart two galaxies are, the more expanding space lies between them, amplifying their apparent separation over time. It also solves a common misconception. There's no center to this expansion, just as no dot on the balloon's surface is the starting point for its stretching. The Big Bang wasn't an explosion in space. It was the explosive expansion of space everywhere at once. But like all analogies, this one has limits. A balloon expands into the surrounding air, while the universe isn't expanding into anything. It's simply growing, with no external void to fill. Still, the core idea holds. Space isn't static. It's dynamic, elastic, and alive with motion we can't see but measure in the redshift of distant starlight. Next time you see a balloon, let it remind you we're all riding the surface of something far grander, a universe stretching its seams in ways we're only beginning to map. But how do we actually measure this relentless expansion of the universe? It's not like we can unspool a cosmic tape measure between galaxies. Enter one of astronomy's most brilliant tricks: standard candles. These celestial objects shine with predictable brightness, acting like lighthouses in the vast ocean of space. Among them, Type 1, a supernova, are the gold standard. When a dense white dwarf star steals too much matter from a companion, it explodes in a cataclysm so uniform, so precisely calibrated, that every single one reaches nearly identical peak brightness. Think of it like nature's own light bulbs, each manufactured to the exact same wattage. This consistency is revolutionary. Since we know their true brightness, we can compare it to how dim they appear from Earth. The greater the dimming, the farther away they are. But here's where it gets even more powerful. By pairing these distance measurements with the redshift of their host galaxies, astronomers create a cosmic speedometer. The supernova reveal how far, the redshift reveals how fast, and together they map the universe's expansion across billions of light years. The real magic happened in the late 1990s when two teams of researchers used these stellar explosions to make an unsettling discovery. Distant supernovae were fainter than expected, implying the universe wasn't just expanding, it was accelerating. It was as if you tossed a ball in the air, expecting it to slow down, only to watch it rocket skyward faster and faster. That shocking revelation earned them the Nobel Prize and introduced the world to dark energy, the phantom force driving this runaway expansion. So next time you hear about the universe's growth, remember, it's all thanks to dying stars that burn with mathematical perfection, lighting our way through the darkness. Without these cosmic mile markers, we'd still be groping in the dark, unaware that space itself is stretching faster with every passing moment. The Hubble constant, it sounds like some unshakable law of nature, a fixed number etched into the fabric of reality. But in astronomy, few things spark more heated debates than this seemingly simple value, the rate at which the universe expands. Here's the twist. Depending on where you look, the universe seems to be growing at different speeds, and this discrepancy isn't just a rounding error. It's a full-blown cosmic mystery that's kept scientists arguing for decades. On one side, we have measurements from nearby galaxies, using tried and true methods like Cepheid variable stars and Type 1, a supernova. These cosmic yardsticks suggest the universe is expanding at about 73 kilometers per second per megaparsec. That means for every 3.26 million light-years you look out into space, galaxies appear to race away 73 kilometers faster every second. It's a number painstakingly refined over a century, backed by mountains of data. But then there's the cosmic microwave background, the faint afterglow of the Big Bang itself. Satellite missions like Planck have mapped this primordial light with breathtaking precision, and their calculations point to a slower expansion, roughly 67 kilometers per second per megaparsec. At first glance, the difference might seem trivial, but in the high-stakes world of cosmology, even a small gap can signal a fundamental flaw in our understanding. So who's right? The answer might be neither, or worse, both. One possibility is that our measurements are missing something, a hidden error skewing the results. But the more thrilling option, that we're staring at evidence of new physics, something beyond our current models. Maybe dark energy isn't constant after all, but changes over time. Or perhaps there's an unknown particle influencing the cosmos in ways we haven't yet imagined. This isn't just academic bickering, it's a clash of cosmic perspectives. Nearby measurements capture the universe as it is today, while the cosmic microwave background reflects its infancy. If they disagree, it's like reading two chapters of the same book and finding contradictory plots. The Hubble constant isn't just a number, it's a riddle wrapped in the vastness of space, and solving it could rewrite the story of everything. If gravity is the universe's glue, pulling everything together with its invisible threads, then dark energy is the exact opposite, a phantom force pushing the cosmos apart at an ever-increasing speed. Picture this: all the stars, galaxies, and even the mysterious dark matter we've spent decades searching for make up just 32% of the universe's total content. The rest, a staggering 68%, belongs to dark energy, an enigmatic presence so dominant it's single-handedly shaping the fate of everything we see. What makes dark energy so bizarre is how it defies gravity's pull. Instead of drawing objects together, it acts like anti-gravity, creating a repulsive effect that stretches space-time itself. Imagine blowing up a balloon with dots on its surface, but instead of the dots just moving apart, the balloon starts inflating faster and faster on its own, no extra breath required. That's dark energy in action, accelerating the universe's expansion with no known mechanism to stop it. The discovery of this force came from observing distant supernovae in the late 1990s. Scientists expected the universe's expansion to slow down over time, as gravity gradually pulled galaxies back toward one another. Instead, they found the opposite. The stretching was speeding up, as if some unseen hand kept pressing the cosmic gas pedal. That's when dark energy entered the spotlight, not just as a minor player, but as the lead actor in the universe's grand narrative. Even now, its nature remains one of physics' greatest puzzles. Some theories suggest dark energy is tied to the vacuum of space itself, a property called the cosmological constant, which Einstein once proposed and later dismissed as his greatest blunder. Others speculate it might be a dynamic field, evolving over time like an invisible tide shifting the cosmos. What's certain is this: dark energy isn't just a footnote in astronomy. It's the force that will ultimately decide whether the universe ends in a frozen, empty drift or tears itself apart in a big rip. For now, all we know is that the cosmos is on a runaway train and dark energy holds the throttle. Every second, it pushes galaxies further into the void, leaving us to wonder what else is hiding in that 68% we can't see. The cosmic microwave background is like a time capsule, a snapshot of the universe when it was just 380,000 years old. This faint glow, often called the afterglow of the Big Bang, blankets the entire sky in microwaves, a relic from the moment the cosmos cooled enough for light to travel freely. But buried within this ancient light are tiny temperature variations, fluctuations no larger than 1 part in 100,000, that tell a startling story. These aren't just random blips, they're the fingerprints of the universe's earliest expansion, patterns etched into the fabric of space itself. Zoom in on these fluctuations and you'll see something extraordinary. Slightly warmer patches represent regions where matter was denser, while cooler spots mark emptier voids. These imperfections might seem minor, but they're the seeds of everything we see today, the gravitational blueprints for galaxies, clusters, and the vast cosmic web. Without them, the universe would be a featureless sea of particles, silent and unchanging. Instead, they reveal how quantum ripples from the Big Bang were stretched by inflation. The universe's explosive initial growth spurt, imprinting themselves onto the cosmos like shadows on a cave wall. The most compelling evidence comes from missions like Planck and WMAP, which mapped these temperature differences with breathtaking precision. Their data shows a pattern eerily consistent with the predictions of cosmic inflation, a rapid expansion that smoothed the universe while amplifying those tiny quantum fluctuations into cosmic-scale structures. It's as if we're reading the universe's baby pictures, decoding the moment it went from a hot, dense soup to something capable of nurturing stars, planets, and eventually us. But here's what's even wilder. The cosmic microwave background doesn't just confirm the universe is expanding. It lets us measure how fast by studying the spacing between these temperature fluctuations. Like the rings of a tree trunk, scientists can calculate the universe's expansion rate with astonishing accuracy. Yet, as we've seen, this clashes with measurements from nearby galaxies, deepening the Hubble tension mystery. The afterglow of creation, it turns out, isn't just a relic of the past. It's a mirror reflecting contradictions that force us to question whether we've missed a fundamental piece of the cosmic puzzle. So the next time you hear static on an old television, remember, about 1% of that noise is the echo of the Big Bang carrying secrets from the dawn of time. It's a whisper from the infant universe telling us how it grew and challenging us to figure out why it's still speeding up. Light doesn't lie. When it travels across the universe, it carries secrets in its color, secrets that reveal how fast distant galaxies are racing away from us. This phenomenon, called redshift, is one of the most powerful tools astronomers have for measuring the expansion of the cosmos. But how does it work? Imagine a police siren speeding past you. As the car approaches, the sound waves compress, making the pitch higher. As it races away, the waves stretch, lowering the pitch. Light behaves the same way. When a galaxy moves toward us, its light gets squeezed into shorter, bluer wavelengths. When it moves away, the light stretches into longer, redder ones like a cosmic rubber band pulled tight. Here's where it gets truly mind-bending. The redshift we see from distant galaxies isn't just caused by their motion through space. It's space itself expanding between us and them, stretching the light as it travels. The longer the journey, the more the light gets stretched. That's why the most distant galaxies show the most extreme redshifts. Their light has been traveling for billions of years, riding an ever-expanding wave of spacetime. It's not just a Doppler effect, it's a cosmological effect, a direct imprint of the universe's growth written into the very fabric of starlight. Astronomers measure this shift with something called a spectroscope, which breaks light into its component colors like a prism. By comparing the positions of familiar chemical fingerprints like the specific wavelengths where hydrogen or oxygen absorb light, they can calculate exactly how much the light has stretched. A galaxy with a redshift of 1, for example, means its light has doubled in wavelength by the time it reaches us. The higher the redshift, the faster the galaxy is receding, and the farther back in time we're looking. But redshift isn't just a speedometer, it's also a time machine. When we observe a galaxy with a redshift of 6, we're seeing it as it was when the universe was just 1 billion years old. The light that left there 12 billion years ago has been stretched so dramatically that what was once ultraviolet or visible light now reaches us as infrared or even radio waves. This is why telescopes like Hubble and James Webb are so crucial. They're designed to catch these ancient, redshifted signals, peeling back the layers of cosmic history like an onion. The implications are profound. Redshift doesn't just confirm the universe is expanding, it lets us trace that expansion across nearly its entire history. Every distant galaxy's light is a message in a bottle, carrying clues about how fast space was stretching when that light began its journey. And when we piece those clues together, they tell a story far stranger than anyone imagined. A story where the expansion isn't just happening but accelerating, driven by forces we're only beginning to comprehend. So next time you hear about redshift, remember, it's not just a color shift, It's the universe's heartbeat, a pulse of light echoing across the ages, showing us how space itself breathes and grows. While much of the universe is rushing apart, our own galactic neighborhood tells a different story, one where gravity still holds sway in an otherwise expanding cosmos. Take the Andromeda Galaxy, our closest spiral neighbor. Unlike nearly every other distant galaxy we observe, Andromeda isn't redshifted, it's actually blueshifted, hurtling toward the Milky Way at a staggering 110 kilometers per second. In about 4.5 billion years, these two titans will collide in a slow-motion dance, merging into a single, colossal galaxy some call Milkdromeda. This cosmic tango defies the broader trend of universal expansion because of something called the local group, a cluster of around 50 galaxies, including the Milky Way, Andromeda, and the Triangulum Galaxy, all bound together by gravity's unbreakable grip. Within this cluster, the gravitational pull between galaxies is so strong it overpowers the expansion of space itself. Imagine two ants clinging to the surface of an inflating balloon. If they hold onto each other tightly enough, the balloon's stretching won't separate them. That's the local group in action, gravity acting as the cosmic glue that keeps our galactic family together. But step beyond this cluster and the story changes dramatically. Galaxies outside our local group are all racing away, their redshifts growing with distance, carried by the relentless expansion of space-time. The Virgo cluster, our nearest large galactic gathering just 55 million light-years away, is already caught in this outward flow, drifting from us as the universe stretches. And the farther out you look, the faster the retreat. It's a startling division, one where gravity wins the battle locally but loses the war on cosmic scales. This duality reveals a profound truth about the universe's structure. Expansion dominates in the vast, empty voids between galactic superclusters where spacetime stretches unimpeded. But in denser regions where galaxies huddle close, gravity resists, creating islands of stability in an ever-widening sea. For now, the Milky Way and Andromeda remain blissfully unaware of the universe's grand expansion, locked in their own gravitational embrace. But eventually, even the local group may find itself isolated, as the space between it and other clusters grows so vast that no future civilization here will ever see another galaxy beyond our own. So while we're safe from cosmic drift for now, the clock is ticking. Every second, the universe grows a little larger, the voids a little emptier, and the islands of galaxies a little farther apart. Our corner of the cosmos is an exception, a pocket where gravity still writes the rules. But beyond our local group, the universe is slipping away, one expanding light-year at a time. One day, the universe will play the ultimate game of hide and seek, and we won't even know we've lost. Right now, our telescopes can peer billions of light-years into space, capturing galaxies so distant their light has traveled since the universe was in its infancy. But that cosmic panorama won't last. As dark energy accelerates the expansion of space, those distant galaxies are slipping away faster than their light can reach us. Imagine standing on a shoreline, watching ships vanish over the horizon, except in this case, the ocean itself is stretching, ensuring no ship ever returns. The math is as chilling as it is inevitable. Today, galaxies beyond about 18 billion light-years are already receding faster than light can bridge the gap, their light forever lost to us. But over time, that boundary will creep inward. In 100 billion years, every galaxy outside our local group will have crossed this cosmic event horizon, their light stretched into wavelengths so long they're undetectable. The night sky won't just look emptier, it will be emptier, leaving future civilizations with a terrifying conclusion. If they only rely on light to study the cosmos, they'll see nothing beyond their own galactic neighborhood. No cosmic microwave background, no redshift patterns, no evidence of the Big Bang. Just an endless void echoing with silence. This isn't science fiction. It's the logical endpoint of runaway expansion, a future where the universe's history gets erased in plain sight. Astronomers call it cosmic isolation, and it poses a haunting question. How many cosmic secrets have already disappeared over the horizon without us realizing? Right now, we're lucky. We live in a golden age of cosmology where the afterglow of the Big Bang is still visible and distant galaxies haven't yet fled beyond reach. But the clock is ticking not in millions of years, but in trillions until the universe's expansion turns our grand cosmic web into a ghost town. Here's the cruel irony. By the time this isolation sets in, the universe will still be teeming with galaxies, stars, and possibly even life. They'll still exist, thriving in their own pockets of space. But the space between them will have stretched so much that no signal, no light, no evidence of their existence will ever reach anyone else. Each island of galaxies will become its own lonely universe, drifting in darkness, unaware of the others. It's as if every civilization is locked in a room with no windows, convinced they're alone, when in reality, the walls between them are just growing thicker. So when you look up tonight, remember this: we're living in a brief, glorious window where the universe still shares its secrets. Future astronomers might dig through ancient data, finding records of galaxies we once saw, and wonder how we ever glimpsed so much. The cosmos is giving us a front row seat to its grandest spectacle, but one day the curtains will close and the show will go on without an audience. To understand what's really happening as the universe expands, we need to untangle a common misconception: the idea that galaxies are simply flying apart through space like shrapnel from an explosion. The truth is far stranger. It's not that objects are moving through space, it's that space itself is stretching, carrying galaxies along for the ride. Think of it like raisins in rising bread dough. The raisins aren't actively moving, they're being pushed apart as the dough expands between them. This is the essence of metric expansion, a concept baked into Einstein's theory of general relativity. Einstein's field equations describe how matter and energy curve spacetime, dictating how objects move within it, but they also reveal something astonishing: spacetime isn't static. It can stretch, warp, or even grow. When applied to the universe as a whole, these equations predict that space itself can expand or contract depending on its contents. In the 1920s, Alexander Friedman solved these equations for a homogeneous universe, one where matter is evenly spread, and found solutions where space must either grow or shrink. Hubble's observations later confirmed the expansion, but the real magic lies in what's actually stretching: the metric. The metric is the mathematical rulebook that defines distances in spacetime. In an expanding universe, this rulebook gets rewritten over time. 2 points at rest relative to each other, like two galaxies not bound by gravity, will still grow farther apart because the space between them is stretching. This isn't motion in the traditional sense. There's no force acting on the galaxies, no energy needed to push them. Instead, the fabric of reality itself is dilating, and the galaxies are just passive passengers. Here's where it gets even weirder. Because expansion is a property of space, it doesn't have a speed limit like objects moving through space. Distant galaxies can appear to recede faster than light, not because they're breaking cosmic speed limits, but because the space between us and them is proliferating. Imagine ants on a rubber rope. If one ant walks at a steady pace while another stretches the rope, the walking ant may never reach the end if the rope stretches faster than it can move. Similarly, light from ultra-distant galaxies struggles to reach us as the space it traverses expands mid-journey, redshifting its wavelength along the way. This distinction between motion through space and the stretching of space is why metric expansion doesn't violate relativity. Special relativity forbids objects from moving through space faster than light, but general relativity permits space itself to expand without such constraints. It's a subtle but crucial difference, one that reshapes how we think about distance, time, and the very nature of the cosmos. The equations also hint at something deeper. If the universe's expansion were purely due to galaxies moving apart, gravity would eventually slow them down. But metric expansion introduces a counterintuitive twist. The more space there is, the more new space can appear, accelerating the process. This is the dark energy puzzle, a phenomenon where empty space itself seems to generate repulsive gravity, pushing the universe apart faster and faster. So when you hear about the universe expanding, remember, it's not an explosion of matter. It's the stretching of spacetime's very fabric, a cosmic ballet choreographed by Einstein's equations, where the stage itself is growing and every galaxy is just along for the ride. Long before galaxies or stars existed, the infant universe was a seething, roiling sea of particles and energy, and it was loud, unimaginably loud. The entire cosmos rang like a bell, with pressure waves rippling through the primordial plasma, compressing and rarefying matter in a rhythmic dance. These weren't just fleeting vibrations, they were sonic booms on a cosmic scale, shock waves that left permanent scars in the structure of the universe. Today, billions of years later, we can still see their echoes imprinted across the sky, fossilized sound waves known as baryon acoustic oscillations, and they're one of our most powerful tools for measuring the universe's expansion. Here's how it works. In the first 400,000 years after the Big Bang, the universe was so hot and dense that photons couldn't travel freely. They kept bumping into electrons, trapped in a chaotic soup with protons and neutrons. But within this soup, gravity tried to pull matter together, while radiation pressure from photons pushed it apart. The result, standing waves of compressed matter, regions where particles clumped together before being pushed outward like ripples from a stone tossed in a pond. Each wave crest became a spherical shell of overdensity, a bubble with a very specific size, about 500,000 light-years across, dictated by how far sound could travel before the universe cooled enough for atoms to form. Then, in a flash, everything changed. When the cosmos cooled to around 3,000 degrees, electrons and protons finally combined into neutral hydrogen atoms, releasing the photons in what we now see as the cosmic microwave background. The sound waves froze in place, their final positions etched into the distribution of matter like cosmic fingerprints. Over billions of years, gravity amplified these subtle overdensities, sculpting them into the galaxies and galaxy clusters we observe today. But here's the genius part, because we know the original size of those frozen waves. They act as a standard ruler stamped across the universe. By measuring how these patterns appear at different distances, and thus different eras in cosmic history, astronomers can track how space has stretched over time. It's like finding a series of identical yardsticks left at various depths in a swimming pool. The ones at the surface appear normal, but the deeper ones look stretched because the water itself has expanded. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing this subtle clustering at scales of roughly 500 million light-years, the grown-up version of those primordial sound waves. What makes baryon acoustic oscillations so valuable is their precision. Unlike supernova or Cepheid variables, which rely on the brightness of individual objects, BAOs measure the large-scale structure of the universe itself, immune to the quirks of any single galaxy. They provide a cosmic ruler that's nearly immune to distortion, letting us measure expansion rates across vast stretches of space and time. And when combined with other probes like the cosmic microwave background, they paint a consistent, if puzzling, picture. The universe isn't just expanding, it's accelerating, with dark energy steadily overwhelming gravity's pull. So the next time you hear about the universe's growth, remember, it's written in sound waves from the dawn of time, a rhythm set in motion when the cosmos was a screaming, boiling plasma, now frozen into the very bones of the cosmos. These oscillations aren't just relics, they're the universe's own measuring tape, letting us stretch our understanding across billions of years with the echoes of its first and only symphony. The expansion of the universe isn't some steady, unchanging march into the void. It's more like a cosmic roller coaster with wild accelerations, sudden slowdowns, and unexpected twists. In its earliest moments, the universe didn't just expand, it exploded, ballooning from smaller than an atom to the size of a grapefruit in a fraction of a second. This was inflation, a burst of hypergrowth driven by a mysterious field that temporarily turned gravity into a repulsive force. For that fleeting instant, space itself stretched faster than light, smoothing out the cosmos like a baker rolling dough until it was nearly perfectly flat. Then, just as suddenly, inflation switched off, dumping its energy into the particles and radiation that would become the universe we know, but the ride was far from over. As the cosmos cooled, gravity took the wheel, slowing the expansion like a cosmic brake. For billions of years, galaxies drifted apart but at an ever-decreasing rate. Imagine tossing a ball into the air. It keeps rising, but gravity gradually saps its momentum until it nearly stops at the peak. That was the universe's deceleration era, a period when matter's gravitational pull seemed poised to eventually halt or even reverse the expansion. Evidence for this slowdown is etched into the cosmic microwave background, where subtle temperature fluctuations reveal how gravity fought to reign in the universe's initial momentum. Then, around 5 billion years ago, something bizarre happened. The expansion didn't just continue, it accelerated, as if the ball suddenly rocketed skyward instead of falling back. This shift wasn't just theoretical. Supernova surveys in the late 1990s captured the telltale dimming of distant stellar explosions, proving the universe was stretching faster than it should be. The culprit, dark energy, a force that behaves like anti-gravity, pushing space apart even as matter tries to pull it together. What's astonishing is how these phases imprint themselves on the cosmos. Inflation left its mark in the cosmic microwave background's eerie uniformity. The slowdown era shaped the distribution of galaxies, with baryon acoustic oscillations preserving the rhythm of those early sound waves. And today's acceleration is written in the emptiness between superclusters, where galaxies flee from one another at ever-increasing speeds. Together, they tell a story of a universe that's never settled, always shifting between phases of growth, each leaving its fingerprints for us to decode. The most puzzling question isn't just why these shifts happened, it's what comes next. Will dark energy keep accelerating the expansion forever, or could it change again, rewriting the rules once more? For now, all we know is this: the universe's expansion rate isn't a constant. It's a saga written in the stretching of space itself. Einstein called it his greatest blunder, a mathematical fudge factor he scribbled into his equations in 1917, then later crossed out in frustration. The cosmological constant was his attempt to make the universe stand still, a counterbalance to gravity that would keep the cosmos from collapsing under its own weight. When Hubble discovered the universe was expanding instead, Einstein dismissed the constant as unnecessary, a clumsy fix for a problem that didn't exist. But history has a way of humbling even geniuses. Decades after his death, that abandoned term would stage a triumphant and unsettling return, reborn as the leading explanation for dark energy. Here's the irony: Einstein's cosmological constant wasn't wrong, it was just ahead of its time. His original idea was simple: empty space isn't truly empty. It seethes with quantum fluctuations, virtual particles flickering in and out of existence. The cosmological constant represented the energy density of this vacuum, a subtle pressure that could, in theory, counteract gravity's pull. What Einstein didn't foresee was that this energy might not just balance the universe, it could dominate it, shoving galaxies apart with relentless force. Fast forward to 1998, when astronomers poring over distant supernova made their bombshell discovery. The universe's expansion wasn't slowing down, it was speeding up. The culprit, something indistinguishable from Einstein's long-discarded constant, a mysterious energy woven into the fabric of space itself. Suddenly, the blunder looked prophetic. The cosmological constant wasn't a mistake. It was a glimpse of dark energy, a force so pervasive it makes up nearly 70% of the universe's total energy budget. Yet the puzzle only deepens from here. Quantum field theory predicts the vacuum energy should be unimaginably stronger, up to 120 orders of magnitude larger than what we observe. This staggering mismatch between prediction and reality is called the cosmological constant problem, and it's one of the most glaring unsolved mysteries in physics. Why is dark energy so weak? Why does it only recently seem to dominate the cosmos? Some theorists suggest the constant isn't really constant. It might evolve over time or interact with other fields in ways we don't yet understand. Others propose radical revisions to gravity itself, frameworks where dark energy emerges from hidden dimensions or modifications to Einstein's equations. The cosmological constant's journey from rejected fix to cornerstone of modern cosmology is a lesson in scientific humility. It reminds us that even our greatest minds can't always foresee which ideas will flourish. Today, as telescopes scan deeper into space and labs probe the quantum vacuum, we're left grappling with Einstein's ghost. His blunder may hold the key to the universe's fate, but unlocking its secrets will require rewriting the rules of physics once again. There's a fundamental limit to how much of the universe we can ever see, not because of our telescope's power, but because of space itself stretching faster than light can traverse it. This boundary is called the observational horizon, and it's not a physical barrier like the edge of a black hole. Instead, it's a shifting line drawn by the relentless expansion of the cosmos, a point beyond which even photons racing toward us at light speed will never arrive. Imagine a marathon runner sprinting toward the finish line, only for the track itself to stretch faster than they can run. No matter how long they persist, the goal recedes endlessly. That's the fate of light from the most distant galaxies. The math behind this is both elegant and sobering. Right now, the observable universe spans about 93 billion light-years in diameter, a sphere centered on Earth containing every photon that's had time to reach us since the Big Bang. But beyond 18 billion light-years or so, galaxies are already receding faster than light due to the expansion of space between us and them. Their light, emitted toward us with desperate hope, is fighting a losing battle against the stretching void. Over time, more and more galaxies will cross this horizon, their final photons arriving increasingly redshifted and faint until eventually their signals cease entirely. Here's what makes this even stranger. Unlike a black hole's event horizon, which moves as you approach it, the observational horizon is shrinking from our perspective. As expansion accelerates, the sphere of reachable light contracts, like a noose tightening around our cosmic view. In a trillion years, any civilizations born in our local group might look up and see only darkness beyond Andromeda, with no evidence of the cosmic microwave background or the billions of galaxies we catalog today. The universe won't have disappeared, it will have stretched itself into invisibility. This raises a haunting question: how much have we already lost? Photons from regions now beyond the horizon may have been emitted shortly after the Big Bang, but will never reach us, their stories forever untold. It's as if we're reading a book where the pages at the edges are constantly dissolving, leaving us with an ever narrower fragment of the full narrative. And the cruel twist: this process isn't symmetrical. From the perspective of a galaxy now crossing our horizon, we are the ones vanishing from their view, receding into a past they can no longer access. Yet within this shrinking theater of observation, there's an odd reassurance. The fact that we can detect this horizon at all, through the redshifting of distant light and the cosmic microwave background's uniformity, means we're living in a privileged sliver of time. We exist late enough to see the afterglow of creation, but early enough to witness galaxies still within reach. Future astronomers may puzzle over ancient data, wondering how we glimpsed so much of a cosmos that to them appears static and lonely. The universe's expansion isn't just shaping its future, It's quietly erasing its past one redshifted photon at a time. Empty space isn't empty. That's the startling truth quantum physics forces us to confront, a truth that might hold the key to dark energy's mystery. According to quantum field theory, what we call a vacuum is actually a seething, bubbling foam of virtual particles. These infinitesimal particles pop in and out of existence so quickly we can't detect them directly, but their fleeting presence leaves behind an unmistakable fingerprint: vacuum energy. This energy, woven into the fabric of space itself, could be the engine driving the universe's accelerating expansion. The math behind this idea is both elegant and frustrating. Quantum mechanics predicts that every cubic centimeter of empty space, no matter how desolate, should contain a staggering amount of vacuum energy, enough to make dark energy seem like a rounding error. But here's where the theory collides with reality. When we calculate the expected value based on known physics, the result is a number 10 to the power of 120 times larger than what we actually observe. It's the worst mismatch between prediction and measurement in all of science, a discrepancy so vast physicists call it the cosmological constant problem. So why does this matter? Because if vacuum energy is real, it could explain dark energy's peculiar behavior. Unlike matter or radiation, which dilute as the universe expands, vacuum energy has a constant density. As space stretches, new space appears, and with it more vacuum energy. This creates a runaway effect where the repulsive force grows in lockstep with the cosmos, perfectly matching the accelerating expansion we've measured. It's as if the universe is filled with an invisible spring, constantly pushing outward with the same unrelenting pressure, no matter how much it stretches. Yet this elegant solution comes with headaches. If quantum vacuum energy is so potent, why doesn't it rip atoms apart or warp space-time beyond recognition? Some theorists propose a loophole: maybe virtual particles cancel each other out almost perfectly, leaving behind only a whisper of their original energy. Others suggest the vacuum's properties have evolved over time, dampening its effects until the modern era. There's even a radical idea that extra dimensions siphon off most of this energy, leaving just enough to drive cosmic acceleration without tearing reality to shreds. The enigma of vacuum energy forces us to confront how little we understand about nothingness. What seems like empty space might be the most dynamic player in the cosmos, humming with hidden forces that shape the universe's fate. Until we bridge the gap between quantum predictions and cosmological observations, this paradox will remain one of physics' greatest unsolved puzzles, a reminder that sometimes the most profound mysteries hide in plain sight, woven into the void itself. Dark energy may dominate our current models of cosmic expansion, but what if we've been approaching the puzzle from the wrong angle? A bold faction of physicists argues that the real culprit isn't some mysterious force, it's our incomplete understanding of gravity itself. These pioneers are rewriting Einstein's playbook with modified gravity theories, frameworks where the rules change on cosmic scales, eliminating the need for dark energy altogether. One of the most compelling alternatives is modified Newtonian dynamics, or MND. Proposed in the 1980s by physicist Mordechai Milgrom, MND suggests that gravity doesn't weaken as quickly over large distances as Newton or Einstein predicted. Instead, at extremely low accelerations like those found in the outskirts of galaxies, gravity gets a subtle boost. This tweak explains why stars in spiral galaxies rotate faster than expected without invoking invisible dark matter, and some versions extend this idea to cosmic expansion, offering an alternative to dark energy. The theory's elegance lies in its simplicity: no undetected particles, just a slight adjustment to how gravity behaves where its pull becomes faint. Then there's F of R gravity, a more mathematically complex approach that alters Einstein's equations by adding terms sensitive to curvature. In these models, empty space generates repulsive gravity naturally when stretched over vast distances, mimicking dark energy's effects without requiring it. Picture a rubber band that stiffens as you pull it instead of inventing a mysterious force to explain why it resists stretching. You're just acknowledging the material's intrinsic properties. Early versions of F of R gravity successfully replicated the universe's accelerating expansion, but they've struggled to explain finer details like the precise clustering of galaxies. Yet none of these theories emerge unscathed. Man's biggest hurdle is the bullet cluster, where colliding galaxies clearly show gravitational effects divorced from visible matter, exactly what dark matter predicts. Modified gravity models also falter when tested against the cosmic microwave background's intricate patterns, which align beautifully with standard cosmology. Even F of R gravity, while mathematically elegant, often requires implausibly fine-tuned parameters to match observations. The tension between these approaches reveals a deeper truth. Our universe is testing the limits of human ingenuity. Whether dark energy or modified gravity ultimately prevails, the debate itself is forcing us to question bedrock assumptions about space, time, and the very nature of reality. Perhaps the answer lies somewhere in between, a radical synthesis we've yet to imagine. For now, these alternative theories stand as daring thought experiments, proving that even our most cherished laws might still be works in progress. The cosmic web is a delicate balancing act, a colossal tug of war between gravity's relentless pull and dark energy's unstoppable push. Picture the universe's large-scale structure as a sponge, with dense threads of galaxies weaving through vast, empty voids. These filaments and voids aren't static. They're locked in a slow-motion battle, their fates dictated by which force wins locally. In the densest regions, where galaxies cluster like cities along a highway, gravity still reigns supreme. Here, mutual attraction keeps galactic superclusters bound together, their collective mass resisting the expansion of space itself. But venture into the voids, the cosmic deserts spanning hundreds of millions of light years, and the story flips. With so little matter to hold them together, these empty regions stretch like taffy, growing emptier and more exaggerated as dark energy accelerates their edges apart. This divergence creates a universe of stark contrasts. Take the Sloan Great Wall, one of the largest known filament structures. Stretching nearly 1.4 billion light-years, it's a gravitational fortress, its galaxies huddled so tightly that expansion can't tear them apart. Yet just beyond it lie voids like Boötes, a spherical abyss so devoid of matter that light crossing it loses energy, redshifted by the relentless stretching of space. The irony is profound. The same force that sculpted these structures, gravity pulling matter into dense webs, now watches helplessly as dark energy hollows out the spaces between them. Over time, this divide will only deepen. Simulations show that while filaments may thin, their cores will remain intact, evolving into isolated island chains in an ever-expanding sea. Voids, meanwhile, will merge like soap bubbles, their boundaries accelerating away faster than any signal could bridge the gap. The result? A future universe where galactic superclusters are the last bastions of structure, adrift in an ocean of nothingness, their light unable to reach one another across the growing darkness. Yet even within these dying embers of structure, gravity's influence isn't uniform. The outer tendrils of filaments already stretched thin will eventually snap, their galaxies severed from the core like boats cut loose from a dock. Astronomers call this process cosmic isolation, and it's already happening at the edges of our observable universe. The Virgo supercluster, our home in the cosmos, will one day be all that's left in our night sky, a lonely archipelago in a void grown too vast to comprehend. What's mesmerizing is how this duality mirrors the universe's earliest moments. The same quantum fluctuations that seeded galaxies also carved the voids, meaning dark energy isn't just erasing structure, it's amplifying an ancient blueprint, stretching the canvas until only the boldest strokes remain. The cosmic web isn't being destroyed, it's being distilled, its essence laid bare by the inexorable expansion of space. And in that distillation, we find a haunting beauty, a universe writing its own epitaph in the language of fading light and growing silence. The Hubble tension isn't just a minor discrepancy, it's a full-blown crisis in cosmology, one that threatens to upend our most fundamental understanding of the universe. At its core lies a simple question with anything but a simple answer. How fast is the universe really expanding? For decades, scientists assumed different measurement methods would eventually converge on a single, definitive value for the Hubble constant. Instead, the gap between them has only widened, leaving astronomers staring down two irreconcilable realities. One camp relies on the cosmic distance ladder, a step-by-step chain of measurements starting with pulsating stars called Cepheid variables in our galactic neighborhood, then jumping to Type 1, a supernova in distant galaxies. These observations suggest an expansion rate of roughly 73 kilometers per second per megaparsec. The other camp studies the cosmic microwave background, the afterglow of the Big Bang, using space telescopes like Planck. Their calculations land closer to 67, a difference that might seem small but carries enormous implications. Imagine two clocks, both meticulously engineered, yet one ticks noticeably faster than the other. Over a few minutes, it's a curiosity. Over billions of years, it reshapes the cosmos. So why does this divide matter? Because these methods aren't just measuring different things, they're measuring different eras of the universe. The distance ladder captures the modern cosmos, a snapshot of today's expansion. The cosmic microwave background, meanwhile, reflects the universe's infancy, its light frozen in time just 380,000 years after the Big Bang. The fact that they disagree suggests something profound. Our standard model of cosmology, the meticulously crafted recipe of dark matter, dark energy, and ordinary matter that's guided astronomy for decades, might be missing a key ingredient. The possibilities are as thrilling as they are unsettling. Maybe dark energy isn't constant but grows stronger over time, throwing off the early universe's calibration. Or perhaps dark matter interacts in ways we haven't accounted for, subtly altering the cosmos's expansion history. There's even a wild card: early dark energy, a hypothetical force that could have surged in the universe's first moments, leaving imprints that skew our measurements. Each of these ideas would rewrite the rules of physics, but here's the catch: none perfectly resolve the tension yet. What's fascinating is how this conflict mirrors historic turning points in science. When Mercury's orbit didn't match Newton's predictions, it wasn't just a math error. It was a clue leading to Einstein's relativity. The Hubble tension could be our generation's Mercury moment, a signal that the universe still holds secrets no model has captured. As new telescopes like the James Webb Space Telescope peer deeper into the cosmos, they're not just searching for answers, they're hunting for the next revolution. One thing's certain: whatever solves this puzzle won't just fill a gap in our equations, it will redefine our place in the cosmos. The universe's expansion could one day turn violent, not with a whimper but with a scream. Among the most chilling scenarios cosmologists have imagined is the Big Rip, a cataclysm where dark energy doesn't just accelerate the cosmos's growth but mutates into something far more sinister: phantom energy. Unlike ordinary dark energy, which maintains a constant density as the universe expands, phantom energy grows stronger over time, its repulsive force intensifying until it overpowers every binding force in nature. Picture a rubber band stretched so taut it doesn't just snap, it shreds itself at the seams. That's the nightmare lurking in the equations, a universe where expansion doesn't just pull galaxies apart but tears atoms, nuclei, and even space-time itself to pieces. The mechanics of this apocalypse are as precise as they are terrifying. Currently, dark energy's push is gentle enough that gravity still holds galaxies and galaxy clusters together. But if dark energy transforms into phantom energy, its density would increase as space expands, creating a feedback loop of destruction. First, galactic superclusters would be ripped apart, their gravitational bonds no match for the accelerating void. Next, individual galaxies would unravel, stars flung into the darkness like sparks from a bonfire. Then, solar systems would disintegrate, planets torn from their orbits. In the final moments, no force in the universe, not electromagnetism, not the strong nuclear force, could resist. Protons would dissolve, quarks would be separated. The fabric of reality itself would fray into meaningless fluctuations. What makes this scenario so haunting is its inevitability, given certain conditions. If phantom energy exists, the countdown is already ticking. Calculations suggest the Big Rip could occur as soon as 22 billion years from now, a blink of an eye on cosmic timescales. Unlike the heat death of the universe, where entropy slowly erases all structure, the Big Rip is a violent, almost personal end, a universe that doesn't fade but is actively dismantled, piece by piece, until nothing remains but isolated particles drifting in an infinite void. Yet there's a twist. For all its horror, the Big Rip might also be the key to detecting phantom energy before it's too late. If this energy exists, its fingerprint should subtly alter how galaxies move today. Telescopes like the Vera C. Rubin Observatory are scanning the skies for anomalies, hints that expansion isn't just accelerating but strengthening over time. Finding such evidence would be both a triumph and a warning, revealing not just the universe's fate but the precariousness of everything we know. The Big Rip remains speculative, a dark whisper in the equations. But its possibility forces us to confront a profound truth. The universe's expansion isn't just a fact, it's a force with the power to create or destroy. Whether it culminates in ice or fire, silence or screams, depends on mysteries we've only begun to unravel. The universe's breakneck expansion today might feel like an anomaly, but its roots stretch all the way back to the very first moments of existence, to a phenomenon so explosive it makes the Big Bang look sluggish by comparison. Cosmic inflation, the universe's primordial growth spurt, saw space itself stretch by a factor of 10 to the power of 26 in less than a trillionth of a second. That's like blowing up a grapefruit to the size of the observable cosmos faster than a beam of light could cross a single atom. And while inflation ended almost as abruptly as it began, its legacy lives on in the gentle, relentless expansion we measure today. The connection between these two epochs, inflation and dark energy, isn't just poetic. Both involve spacetime stretching under the influence of repulsive gravity, a phenomenon where empty space exerts negative pressure. During inflation, this push came from a hypothetical field called the inflaton, which flooded the universe with energy before decaying into the particles we know. Today, dark energy, or perhaps a resurrected cosmological constant, plays a similar role, albeit at a far weaker strength. It's as if the universe traded its youthful, frenetic growth for a slower, steadier stride, but never lost its appetite for expansion. Evidence for this continuity is etched into the cosmos itself. Inflation's rapid stretching ironed out the universe's wrinkles, leaving it nearly perfectly smooth, a flatness we still observe in the cosmic microwave background. Quantum fluctuations during that hypergrowth seeded all future structure, imprinting the faint temperature variations that later grew into galaxies. Without inflation's explosive start, the universe might have collapsed back on itself or torn apart too quickly for stars to form. Instead, it struck a delicate balance, one that set the stage for dark energy to take over billions of years later. Yet mysteries linger. Why did inflation end? Could dark energy be some dormant remnant of the inflaton field, reawakening after eons of silence? Some theories even suggest multiple inflationary phases, with our current acceleration marking the dawn of a new cycle. While these ideas remain speculative, they underscore a profound truth. The universe's expansion isn't a single event but a story written in chapters, each revealing new twists in spacetime's behavior. The most tantalizing clue linking past and present lies in their shared unpredictability. Just as inflations trigger and shut down defy classical physics, dark energy's origin and future evolution resist tidy explanations. Both epochs remind us that empty space is anything but passive. It's a dynamic stage, capable of sudden, violent transformations or slow, inexorable shifts. Whether these phases are truly connected or merely cosmic coincidences, they force us to confront how little we understand about the forces shaping reality. So when you hear about the universe's expansion today, remember, it's not just a modern phenomenon. It's the latest verse in a song that began nearly 14 billion years ago when space-time first learned how to stretch. The universe owes its spectacular diversity, galaxies, stars, even planets, to something almost absurdly small: quantum fluctuations, ghostly ripples in the fabric of reality at scales a billion times tinier than an atom. In the first moments after the Big Bang, these microscopic hiccups in energy density were stretched to staggering proportions by the universe's explosive expansion, transforming from subatomic whispers to cosmic blueprints that dictated where galaxies would cluster and where vast voids would yawn. Picture the infant universe as a pot of water just before it boils. Tiny bubbles form and vanish at random, each a fleeting imbalance of energy. Now imagine that pot suddenly expanding to the size of an ocean, freezing those bubbles in place as they grow to the scale of continents. That's what inflation, the universe's exponential growth spurt, did to quantum fluctuations. What were once quantum jitters smaller than a proton became density variations spanning light years, their patterns imprinted onto the hot plasma of the early cosmos like shadows cast by an unseen hand. These amplified ripples didn't just linger, they became gravitational wells, subtle dips in space-time where matter began to pool. Slightly denser regions pulled in more gas through gravity, while emptier zones thinned further. Over billions of years, this cosmic feedback loop turned those initial wrinkles into the galaxies and superclusters we see today. The cosmic microwave background captures this moment perfectly. Its temperature variations, mapped by satellites like Planck, show the exact spots where these quantum seeds began their journey toward becoming galactic metropolises. The wonder isn't just that quantum effects could shape something so vast. It's that their signature remains mathematically precise. The distribution of galaxies across the sky today mirrors the statistical spread of those primordial quantum fluctuations with eerie accuracy, like finding the fingerprint of a subatomic particle on the surface of a planet. This connection between the infinitesimal and the infinite is one of cosmology's most profound revelations. The universe's largest structures are at heart quantum mechanics writ large. Yet this process wasn't uniform. Some fluctuations stretched more than others, creating a hierarchy of structures. The tiniest ripples birthed star clusters and dwarf galaxies, while larger ones sculpted galaxy filaments and superclusters. Even now, these variations echo in the way galaxies spin and cluster, their motions tracing back to quantum randomness frozen in time by expansion. What's staggering is how contingent it all was. Without inflation's lightning-fast stretching, those quantum seeds would have remained microscopic, lost to the noise of thermal motion. The universe might have ended up smooth and lifeless, a featureless sea of particles. Instead, expansion acted like a cosmic amplifier, turning whispers into thunder, a reminder that the richness of the cosmos hinges on events so fleeting, so minuscule, they defy ordinary perception. So when you gaze at the night sky, remember, you're not just seeing stars, you're seeing quantum mechanics magnified to cosmic proportions by the universe's relentless growth. If the universe is infinite and filled with stars, why isn't the night sky blindingly bright? This deceptively simple question, known as Olber's paradox, haunted astronomers for centuries. The answer lies in one of the most profound truths about our cosmos, its relentless expansion. Picture this: every point in space should, in theory, eventually lead to a star if the universe is endless and unchanging. Like standing in an infinite forest where every gap between trees is filled by another tree, the entire sky ought to blaze with starlight, but it doesn't. The darkness between stars isn't just empty space, it's a testament to the fact that the universe is dynamic, evolving, and stretching itself thin. Here's how expansion solves the riddle. As light travels across the cosmos, space itself is expanding beneath it, stretching the wavelengths of photons like taffy. The farther the light journeys, the more it's redshifted, drained of energy until it slips from visible light into infrared, then radio waves, and eventually into near nothingness. The most distant stars and galaxies don't just fade, they vanish from our view entirely. Their light stretched beyond the limits of detection, but that's not the only factor at play. The universe also has a finite age, about 13.8 billion years. Light from stars beyond a certain distance simply hasn't had time to reach us yet. Even if the cosmos is infinite, we're surrounded by a cosmic horizon, a sphere beyond which no signal can yet penetrate. Combine this with redshifting, and the night sky's darkness transforms from a paradox into a revelation, a signature of the universe's youth and its headlong rush into expansion. There's an even deeper layer to this story. Expansion doesn't just hide distant starlight, it erases it. As the universe accelerates, galaxies now visible will one day cross an event horizon, their light forever lost to the stretching void. Future civilizations might gaze into a sky bereft of all but the nearest stars, unaware of the vast cosmic tapestry we still glimpse today. So the next time you look up at the night sky, don't just see the darkness as emptiness. See it as a cosmic clock counting down the finite time we have to witness the universe's grandeur before expansion carries it all away. The stars we see are the lucky ones, the ones still close enough, still bright enough to remind us that light, like time itself, is fleeting. Among the countless stars dotting the night sky, a special class of pulsating giants holds the key to measuring the universe's expansion with astonishing precision. Cepheid variables, stars that rhythmically brighten and dim like cosmic lighthouses, have been astronomy's gold standard for measuring intergalactic distances for over a century. Their secret lies in a brilliant correlation discovered by Henrietta Swan Leavitt in 1912. The longer a Cepheid takes to pulse, the brighter it truly is. This period luminosity relationship transforms these stars into nature's perfect yardsticks. Once you time their flicker, you know their actual brightness, allowing astronomers to calculate distances by comparing that intrinsic glow to how dim they appear from Earth. When Edwin Hubble first trained his telescope on Cepheids in the Andromeda Galaxy, he wasn't just proving it lay beyond the Milky Way, he was laying the groundwork for modern cosmology. Today, the Hubble Space Telescope, named in his honor, uses these same stars to calibrate the cosmic distance ladder with millimeter precision. By observing Cepheids in galaxies relatively close to ours, astronomers anchor their measurements to a concrete foundation before leaping to more distant supernovae. It's like marking precise intervals on a ruler before attempting to measure a mountain. The process is both delicate and demanding. Hubble's sharp eye can isolate individual Cepheids in galaxies up to 100 million light-years away, tracking their pulsations over weeks or months. Each flicker is meticulously timed, its period matched against Leavitt's law to determine the star's true luminosity. The difference between that known brightness and its apparent dimness reveals the distance, much like estimating how far away a car is by the fading of its headlights. But Cepheids aren't just cosmic mileposts, they're time capsules. Their pulsations encode information about their age, composition, and even the dust between us and them that might skew measurements. Modern techniques account for these variables by observing Cepheids at multiple wavelengths, from visible light to infrared, peeling back layers of interference to reveal their pure signal. This cross-checking has refined distance measurements to within a few percentage points, an incredible feat considering we're gauging spans so vast they defy human intuition. What makes Cepheids indispensable to the Hubble tension debate is their dual role. They not only measure distances to nearby galaxies, but also calibrate the brightness of Type 1, a supernova farther out. By stitching these measurements together, astronomers construct a continuous chain from our cosmic backyard to the edge of the observable universe. Yet here lies the rub when Cepheid-based distances clash with predictions from the cosmic microwave background. The discrepancy forces us to question whether our ruler might have hidden kinks or if the universe itself is playing tricks on us. These pulsing stars are more than just tools. They're silent witnesses to one of science's greatest detective stories. Every flicker carries echoes of Henrietta Leavitt's insight, Edwin Hubble's boldness, and the relentless curiosity that drives us to map the unthinkable. As telescopes grow sharper and methods more refined, Cepheids remain steadfast guides in our quest not just to measure space, but to understand why it stretches the way it does. The light from distant supernova doesn't just tell us how far away they are, it carries hidden clues about time itself. When astronomers observe these stellar explosions billions of light-years away, they notice something peculiar. The explosions seem to unfold in slow motion. A supernova that typically brightens and fades over weeks might appear to stretch across months when viewed across cosmic distances. This isn't a trick of the light or flawed observations. It's direct evidence that the universe's expansion warps time as profoundly as it stretches space. Here's why this happens. As light travels from an exploding star toward Earth, the space between us and the supernova is continually expanding like a treadmill set to cosmic speeds. Photons emitted later in the explosion have to traverse more stretched space than their predecessors, delaying their arrival. The result, a time lag effect where the supernova's light curve. The graph of its brightening and fading appears dilated, stretched out like audio played at half speed. The degree of this time dilation matches perfectly with the redshift of the supernova's light, providing independent confirmation that space itself is stretching. This phenomenon serves as a powerful cross-check for expansion measurements. While redshift tells us how much wavelengths have stretched, time dilation reveals how much the fabric of spacetime has expanded during the light's journey. Like two witnesses corroborating the same story, these effects must align if our understanding of cosmic expansion is correct, and they do spectacularly. When researchers analyzed Type 1, a supernova, they found their stretched light curves precisely matched the predicted time dilation for their redshifts. It's as if the universe left a built-in verification code in the very explosions we use to measure it. The implications run deep. Time dilation in supernova isn't just a curiosity, it's a direct consequence of relativity where time and space are interwoven. The fact that we observe this effect across billions of light-years confirms that expansion isn't some local fluke, it's a fundamental property of spacetime itself. Every slowed-down supernova is a cosmic hourglass, its grains of light falling at a pace dictated by the stretching universe. What's equally fascinating is how this effect scales with distance. A supernova at redshift 1, meaning its light has doubled in wavelength, will appear to unfold twice as slowly as one nearby. At redshift 2, time stretches to 3 times its normal flow. This predictable relationship allows astronomers to use time dilation as a ruler, measuring cosmic distances without relying on brightness alone. It's a rare example where relativity's stranger predictions become essential tools for mapping the cosmos. Yet this phenomenon also highlights a paradox. While we perceive these distant explosions in slow motion, from the perspective of the supernova itself, time flowed normally. The star lived and died at its own pace, unaware that its final moments would be stretched into eternity for faraway observers. In this way, every supernova is both a beacon and a time capsule, its light carrying not just spatial but temporal fingerprints of the universe's expansion. And as we decipher these signals, we're not just measuring space, we're watching time itself bend to the will of an expanding cosmos. The universe doesn't play favorites, at least not on the grandest scales. This foundational idea, known as the cosmological principle, declares that no matter where you stand in the cosmos or which direction you gaze, the large-scale structure of the universe should look essentially the same. It's a bold assumption, one that underpins nearly every modern cosmological model. But how do we know it's true? The answer lies in the relentless uniformity of the universe's expansion, a phenomenon so consistent it's as if space itself is following an unbreakable rulebook. Picture standing in an infinite forest where every tree grows at the same rate. From your vantage point, trees farther away would appear to recede faster than nearby ones, not because they're moving faster through the forest, but because there's more expanding space between you and them. Now replace trees with galaxies, and you've got Hubble's law in action, the observation that galaxies' recession speeds scale perfectly with their distances. This isn't just a fluke of our local cosmic neighborhood. From every galaxy's perspective, the pattern holds. Observers in Andromeda, the Virgo cluster, or a galaxy billions of light years away would all report the same thing. Everything seems to be moving away from them, with speeds increasing linearly with distance. This uniformity is the cosmological principle in motion. If matter were clumped unevenly, if some regions of space were denser or emptier on the largest scales, we'd see telltale variations in expansion rates. Gravity from overdense regions would slow local expansion, while voids might stretch faster under less resistance. Yet when astronomers map the cosmos, they find expansion's rhythm is eerily consistent in all directions, like a symphony where every instrument plays in perfect sync. Even the cosmic microwave background, that fossilized light from the universe's infancy, reveals temperature variations of just 1 part in 100,000, evidence that matter was distributed with near-perfect smoothness when the cosmos was a seething plasma. The implications are profound. This isotropic expansion suggests the universe lacks a center or an edge, much like the surface of a balloon has no middle point as it inflates. It also hints that the laws of physics operate uniformly everywhere, a principle so trusted that astronomers use it to calibrate their deepest observations. When the James Webb Space Telescope peers at galaxies billions of light years away, it assumes their physics, their atomic emissions, their gravitational behaviors mirror what we see nearby. Without this cosmic democracy, we'd have no baseline for interpreting distant light or reconstructing the universe's history. Yet the principle isn't without challenges. Some studies hint at a possible axis of evil, a direction in space where expansion rates or CMB temperatures might deviate slightly. Others point to colossal structures like the Hercules Corona Borealis Great Wall, a filament of galaxies stretching 10 billion light-years, seemingly defying the expected scale of homogeneity. Are these anomalies statistical noise or cracks in cosmology's bedrock? For now, the weight of evidence, from supernova surveys to galaxy clustering, still overwhelmingly favors a universe that's smooth in its grand design. This doesn't mean the cosmos is boringly featureless. Just as an ocean appears flat from a satellite but roils with waves up close, the universe teems with galaxies, clusters, and voids on small scales of millions of light-years. But zoom out far enough, and these fluctuations average out, leaving a tapestry so uniform it could only be woven by expansion's impartial hand. The cosmological principle isn't just a philosophical stance, it's a prediction relentlessly tested and confirmed by the universe's own behavior, written in the redshift of distant starlight and the echo of the Big Bang itself. So when you hear that space is expanding, remember, it's not stretching chaotically, it's following a deeper order, one that treats every observer in every galaxy to the same breathtaking view of a cosmos that plays by the same rules everywhere. And that's not just convenient for astronomers, it's a clue that the universe, for all its complexity, is built on foundations of astonishing simplicity. Right now, humanity's view of cosmic expansion is like peering through a keyhole, but that keyhole is about to be blown wide open. The James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope represent a quantum leap in our ability to measure the universe's growth, armed with infrared vision sharp enough to spot the first galaxies ever born. Where Hubble gave us glimpses, these next-generation observatories will deliver encyclopedias, capturing light so ancient it's been stretched nearly to invisibility by 13 billion years of cosmic expansion. JWST revolutionary infrared detectors are already rewriting the rules. By observing galaxies at redshifts beyond 10 objects so distant their light was emitted when the universe was less than 5% of its current age, it's tracing the expansion rate's evolution across nearly the entire cosmic timeline. But here's the game changer. JWST isn't just seeing these ultra-distant galaxies, it's dissecting them with spectroscopic precision. By splitting their light into rainbows, astronomers can measure each galaxy's exact redshift, eliminating guesswork and revealing how fast space was stretching at different epochs. Imagine having a time lapse of the universe's growth instead of just snapshots. That's the power of JWST multi-object spectrograph, which can analyze hundreds of galaxies simultaneously. Then there's the Roman Space Telescope, set to launch in the mid-2020s. While JWST zooms in on exquisite details, Roman will pull back for the ultimate wide-angle view. Its wide-field instrument will survey the sky 100 times faster than Hubble, cataloging billions of galaxies across 10,000 square degrees, about a quarter of the observable universe. This avalanche of data will map baryon acoustic oscillations with unprecedented resolution, using those frozen sound waves as a cosmic ruler stretching back to the universe's toddler years. But Roman's real magic lies in its synergy with JWST. While JWST identifies the most distant galaxies, Roman will statistically analyze their clustering patterns across vast volumes of space, revealing how dark energy's push has varied over billions of years. What makes these telescopes so transformative is their ability to cross-examine expansion history from multiple angles. Supernova, baryon oscillations, redshift surveys, each method has strengths and blind spots. But combine JWST pristine distant galaxy spectra with Roman's enormous statistical samples, and you've got a cosmic triangulation system that could finally resolve the Hubble tension. Maybe early galaxies moved differently than predicted, hinting at unknown physics. Perhaps dark energy's strength has changed over time, leaving subtle fingerprints in the growth of large-scale structure. These telescopes aren't just upgrading our instruments, they're rewriting the investigation. And the discoveries won't stop there. Both telescopes will spot primordial galaxies so pristine they've barely been altered by cosmic evolution, offering snapshots of the universe before dark energy dominated. Roman's gravitational lensing surveys will map dark matter's distribution in 3D, showing how its gravitational scaffolding has been stretched and warped by expansion. JWST might even catch population 3 stars, the universe's first stellar generation whose extreme redshifts could test expansion models where no telescope has looked before. We're standing on the threshold of a new cosmic census, one that will measure the universe's pulse across 95% of its history. The answers won't just refine a number, they'll challenge our understanding of gravity, space-time, and the very nature of dark energy. When future textbooks describe the 21st century's great astronomical revolutions, this era where we moved from observing expansion to truly understanding it will shine as bright as the galaxies these telescopes were built to find. Dark energy isn't just a mysterious force, it's a cosmic wildcard, and its true nature is locked inside a single, deceptively simple symbol, W. This parameter, known as the equation of state, dictates whether dark energy is a constant presence, a dynamic field, or something even stranger. Think of it as the universe's thermostat, controlling how fiercely dark energy pushes against gravity's grip, and ultimately whether the cosmos ends in ice, fire, or something beyond our imagination. The math behind this is both elegant and profound. In cosmology, the equation of state relates a substance's pressure to its energy density, with W as the proportionality factor. For dark energy, W equals the ratio of its pressure to its energy density. Here's where it gets fascinating. If W is exactly -1, dark energy behaves like Einstein's cosmological constant, a steady, unchanging force woven into the fabric of space itself. This scenario leads to the Big Freeze, where galaxies drift apart so relentlessly that star formation sputters out, leaving the universe cold and dark. But W might not be so predictable. If it's slightly more negative than -1, say -1.1, dark energy's push grows stronger as space expands, a scenario dubbed phantom energy. This is the nightmare fuel behind the Big Rip, where galaxies, stars, and even atoms are torn apart by runaway expansion. Conversely, if W is less negative, maybe -0.9, dark energy could weaken over time, allowing gravity to eventually halt the expansion or even reverse it in a big crunch. The universe's fate hinges on this single number, and we're still not sure where it falls. Measuring W is one of cosmology's greatest challenges. Astronomers hunt for clues in supernovae, baryon acoustic oscillations, and the cosmic microwave background, each method offering a piece of the puzzle. The latest data suggests W is tantalizingly close to -1, but with enough uncertainty to leave room for drama. The Euclid Space Telescope, launched in 2023, is designed to pin down W with unprecedented precision by mapping billions of galaxies. Its findings could confirm our darkest cosmic suspicions or force us to rewrite physics once again. What's most thrilling is how delicate this balance is. A shift in W of just 0.1 could mean the difference between a universe that expands forever and one that self-destructs. It's as if the cosmos is balanced on a knife's edge, with dark energy's equation of state holding the scales. And while we don't yet know where it will lead, one thing's certain: the answer lies in the void, hidden in the stretching of space itself, waiting for us to decode its final message. The universe's expansion might feel like a cosmic-scale phenomenon, but its origins could lie in the tiniest corners of reality, where gravity and quantum mechanics collide in a battle for supremacy. These two titans of physics have refused to reconcile for over a century, leaving a glaring hole in our understanding of the universe's most fundamental behavior. Yet hidden within that conflict could be the keys to explaining why space stretches at all, and why dark energy behaves so mysteriously. Imagine space-time not as a smooth, unbroken fabric, but as a frothing sea of quantum foam, where microscopic wormholes blink in and out of existence and space itself fractures into discrete pixels at the Planck scale. In this chaotic subatomic arena, gravity isn't the gentle curvature of Einstein's relativity, it's a seething storm of virtual particles exchanging gravitons, the hypothetical carriers of gravitational force. Some theories suggest that this quantum turbulence generates a repulsive effect, like bubbles in boiling water pushing upward, driving space apart at its most fundamental level. String theory, one of the leading candidates for quantum gravity, paints an even wilder picture. It proposes that the universe's vacuum energy, the same energy that might fuel dark energy, arises from the vibrations of unimaginably tiny strings threading through higher dimensions. The way these strings stretch, fold, and resonate could dictate how spacetime itself expands, with certain vibrational modes acting as cosmic accelerants. If true, dark energy might not be some exotic substance but the harmonic hum of strings tuned to the frequency of expansion. Loop quantum gravity takes a different approach, suggesting space is woven from interconnected loops that form a dynamic, ever-changing network. As these loops shift and reconfigure, they could generate an emergent expansion, like a sweater stretching because its stitches rearrange. Intriguingly, Some loop quantum cosmology models predict that the universe didn't just emerge from a singularity but bounced from a previous collapsing phase, with expansion encoded in the rebound's quantum geometry. Even if these theories remain speculative, they share a tantalizing thread. Expansion might not require dark energy as an external force. Instead, it could be spacetime's innate quantum behavior writ large, a collective effect of countless microscopic interactions. Picture a crowd at a concert. No single person decides the wave's motion, yet their combined actions create a sweeping pattern. Similarly, the universe's growth could be the sum of trillions of quantum events, each nudging space outward in ways we're only beginning to fathom. The implications are staggering. If quantum gravity explains expansion, it might also reveal why dark energy's density is so perplexingly low, a fluke of vibrational harmonics or loop configurations. It could even hint at a deeper connection between inflation's explosive beginnings and today's acceleration, two epochs united by quantum processes we've yet to untangle. For now, these ideas lie at the frontier of theoretical physics, where equations outstrip experiments and imagination races ahead of evidence, but the hunt for answers is accelerating. Next-generation gravitational wave detectors might catch whispers of quantum spacetime's granularity, while tabletop experiments probe whether vacuum energy fluctuates as predicted. Every new clue brings us closer to answering the ultimate question: is expansion something the universe does, or something it fundamentally is? The answer, when it comes, won't just solve a cosmic mystery. It could rewrite reality's rules from the ground up. What if our universe isn't the only one stretching into the void? Among the most radical explanations for cosmic expansion lies a mind-bending idea: that we're just one bubble in an endless multiverse froth, each universe inflating like a soap bubble in an infinite cosmic sink. This isn't science fiction. Eternal inflation, a theory extending the Big Bang's initial hypergrowth, suggests that the same repulsive gravity that once ballooned our universe could still be spawning new ones beyond our horizon, each with its own physics, its own destiny. Imagine a pot of water boiling endlessly, with steam bubbles forming, rising, and drifting apart. In this metaphor, each bubble is a separate universe, its surface tension defined by the energy fields that birthed it. Our universe's expansion might simply be the aftermath of our bubble's nucleation, one inflationary pocket among countless others, forever hidden from view by the exponential stretching of space between them. The kicker: dark energy's eerie uniformity could be a relic of this process, a fingerprint of the conditions when our bubble first froze into existence. The math behind this is both elegant and daunting. Eternal inflation hinges on quantum fluctuations, tiny energy hiccups that spawn new inflationary regions within an ever-expanding quantum foam. Most of these regions continue inflating, but occasionally one decays into a stable universe like ours, its energy converting into the hot soup of particles we recognize. The result is a self-replicating fractal of universes, each with random physical constants. Some might collapse instantly, others could harbor life. Ours just happens to have the right balance for galaxies and us to exist. Critics argue this is untestable metaphysics, but subtle clues might lurk in the cosmic microwave background. Anomalies like the cold spot, a strangely frigid patch of sky, could be bruises from a long-ago collision with another universe. Or perhaps the cosmological constant's perplexingly small value isn't fine-tuned. It's just the luck of the draw in a multiverse where every possible value exists somewhere. Even dark energy's acceleration could reflect our bubble's slow merger with a neighboring one, a cosmic undertow tugging at spacetime itself. Yet the boldest implication isn't about other universes, it's about time. If eternal inflation is true, our Big Bang wasn't the beginning. It was a local event in an eternal sequence, a single note in a symphony without end. The expansion we measure today might not just shape our universe's fate, It could be the faint echo of a process without origin, without finale, where beginnings and endings are just transitions in an infinite cosmic dance. For now, these ideas linger at the edge of science, where speculation brushes against observation. But as telescopes probe deeper and theories sharpen, we might one day find evidence that our universe's expansion isn't just a solo performance, it's part of an ensemble too vast to comprehend, hidden beyond the stretch of space we'll ever see. The universe's fate isn't written in the stars, it's etched into the fabric of space itself, encoded in the relentless expansion we've spent centuries trying to measure. Every redshifted galaxy, every dimmed supernova, every whisper of the cosmic microwave background adds another piece to this puzzle, pointing toward one of three possible endings. The first is the heat death, a slow, silent expiration where expansion stretches matter so thin that stars burn out, black holes evaporate, and the cosmos fades into a uniform, lifeless chill. Picture an ember cooling in an ever-growing void, its heat dissipating across a space so vast that no two particles ever meet again. This scenario hinges on dark energy remaining constant, its push steady but never strengthening, allowing gravity to maintain cosmic structures locally even as the gaps between them grow insurmountable. But dark energy might not play fair. If it evolves into phantom energy, gaining strength as space expands, the result is the Big Rip, a cosmic shredding where galaxies, stars, and even atoms are torn apart by exponential expansion. Imagine spacetime as a rubber sheet pulled so taut that first galaxies, then solar systems, then molecules are ripped from one another. The final moments would be apocalyptic, nuclei disintegrate, and spacetime itself fractures into quantum foam. Time would lose all meaning in a universe where no 2 points can interact, leaving behind a desolate landscape of isolated particles drifting in infinite emptiness. Between these extremes lies the Big Crunch, a dramatic reversal where gravity finally triumphs. If dark energy weakens over time or matter's gravitational pull exceeds expansion speed, the universe could collapse back into a singularity, a mirror of the Big Bang in reverse. Galaxies would blueshift as they hurtle toward one another, cosmic background radiation heating up until space becomes a searing plasma. The irony, this fiery finale might birth a new universe in a cyclical rebound, echoing theories of eternal inflation where every collapse ignites another expansion. The deciding factor isn't just today's expansion rate, it's how that rate changes over time. Precise measurements of distant supernova and baryon acoustic oscillations reveal whether dark energy's push is steady, strengthening, or waning. Even subtle shifts in the equation of state parameter, whether W equals -1, dips below it, or rises toward 0, could tip the scales between freeze, rip, or crunch. Current evidence slightly favors heat death, but with margins of error that leave room for cosmic surprises. What's haunting is how little time we might have left to solve this riddle. As expansion accelerates, evidence slips beyond our grasp, galaxies vanishing over the observational horizon, their light stretched into undetectability. Future astronomers may lack the data we take for granted, their view narrowed to a shrinking pocket of the cosmos. Our era is a fleeting golden age for cosmology, perched between the afterglow of the Big Bang and the encroaching darkness. Yet in this uncertainty lies a profound beauty. The universe's fate isn't predetermined. It's a dynamic equation where every measurement refines the answer. Whether it ends in ice, fire, or silence, our quest to understand it binds us to the cosmos not just as observers, but as participants in a story 13 billion years in the telling. The expansion rate isn't just a number, it's the universe's heartbeat, and its rhythm holds the secret of how it all ends. From the echoes of the Big Bang to galaxies vanishing over the cosmic horizon, we've journeyed through 30 astonishing truths about the universe's expansion, each more mind-bending than the last. We've seen how space stretches like an infinite rubber sheet, carrying galaxies apart faster than light can bridge the gaps. We've watched dark energy rewrite the rules of gravity, turning empty space into an unstoppable force. We've traced quantum ripples from the universe's first moments to the sprawling cosmic web we see today. And yet, for every answer, a dozen new questions erupt like supernova in the night. Consider this: we live in a fleeting golden age of cosmology, where the afterglow of creation is still visible, and distant galaxies haven't yet fled beyond our view. Future civilizations might gaze into a sky stripped of all but the nearest stars, their textbooks filled with relics of a cosmos we once glimpsed in its prime. That's the paradox of our expanding universe. The more we learn, the more we realize how much is slipping away, hidden behind the relentless stretching of space. But here's the wonder: every atom in your body, every star in the sky, is part of this grand, accelerating dance. The same expansion that will one day isolate galaxies also made life possible, spreading matter just thinly enough for stars to form, planets to coalesce, and curiosity to ignite. We're not just observers of this story, we're characters in it, stardust given consciousness, trying to decode the universe that made us. The mysteries ahead are as vast as the voids between galaxies. Is dark energy constant, or will it evolve? Are we alone in this bubble of space-time, or is ours just one universe in an infinite multiverse? The answers lie in the redshift of distant supernova, the whispers of gravitational waves, and the quantum hum of empty space itself. So keep looking up. The night sky isn't just a ceiling, it's a window into a cosmos that's growing, changing, and daring us to keep exploring. If you're as captivated by these cosmic mysteries as we are, hit subscribe and join us for the next chapter. The universe is expanding, but the adventure is just beginning.